Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 27. We're doing multiple regression. We're in chapter 8. This is part 3. Last time we looked at the assumptions. It's the same 5 labeled assumptions as we had under straight line regression, but there's some major differences in that we're using multiple variables instead of just one. And so we have to talk about the set of values for the k x variables or predictor variables, and so we have to talk about that set of variables at one time. And when it comes to linearity, we're not talking straight line anymore, we're talking a linear combination, which can be any shape. So this time we're going to talk about determining the best equation. Next time we'll talk about the ANOVA table and some examples, but this time we're going to talk about how we determine the best equation. And so you may not be very surprised to hear that we're going to use least squares, not least squares, but least squares method for determining the best fitting, and it's not straight line, the best fitting line or plane that minimizes the sum of squares of the deviations or vertical distances. So again, we're going to minimize the sum of squares of errors. So SSE is what we're going to minimize here. And if what we're going to want to minimize is that's SSE is the sum of squares of y minus yi hat. So I'll zoom in so maybe you can see that a little better. And if we plug in for yi hat, then we plug in the regression equation, but hat, with the yi hat, there's no error term. When it's just y, then we have an error term. When we're doing the expected or mean value, or we're doing fitted, we no longer have betas, we have beta hats here. So that's why we don't have the error term in this. But we replace yi hat with its expression, which is the regression line here, yi minus that. So yi's are the actual observed y values. Now let's give a little matrix notation. This says matrices, and technically that's correct because these vectors are matrices with, in this case, n by 1. So it's n rows, 1 column. And this would be, let's see, nk plus 1. Let's see, n plus 1 k, all right, by k. Okay, so it's n by k plus 1 columns, right? N by k plus 1 columns, because we have this 1 here, and then we have k variables here. All right, so what we're going to do is we would write this equation as y is equal to x beta plus epsilon. Now epsilon, so what happens when we multiply x and beta is we use matrix multiplication. So this row gets multiplied by this column. So the 1 gets multiplied by the beta naught, the x1 gets multiplied by beta 1, and then we add those, and then finally we take this times this, so the beta k times the x1k, and we get an equation. So for every row of x, we end up with an equation. Oh, and since we're adding epsilon, we'll add this to that. So this will look like, say, beta naught plus beta 1 x11 plus all the way down to beta k x1k plus epsilon. And then we'll have, in this case, n rows, because we've got a sample of size n. So each one of these rows represents a point, a sample of points. So we have a y value, and we'll have the x values, okay? So when I write this big, bold beta, that means that we are talking about the vector, okay? So the vector beta, which includes all the beta values, we can now view beta hat. Now, not beta. Beta is a constant, but beta hat can be viewed as a random variable because we can solve this equation here for beta hat when we have y hat. Okay, so no y hat there. So let me write this. So we could have y hat would equal x beta hat. So we can solve for beta hat. And when we do that, we have to solve this a special way. So this would be x inverse y hat equals beta hat. We have to be, the order is important, and the notation is very important. Those of you who know linear algebra, you may be familiar with this. If you don't worry too much about the matrix part. We're not going to do anything with it in this course because this is an applied course. But I do want to explain it. So we can view beta hat as a linear function of y. Well, x certainly is not a random variable. Those are fixed values, remember. They're predictor variables, but they're fixed, so they're not really random at all. So if I view beta as a function of y hat, now beta is a random variable. And since y is normally distributed, so are the beta hats. And that means all of the beta hats. That means beta naught hat, beta 1 hat, all the way up to beta k hat. So the least squares, so we can do that. And remember that these are all, each of the individual ones are normally distributed because y is normally distributed. So there's a theorem that says the sum of normally distributed random variables is also normally distributed. You can't do that with other random variables, but you can with the normal, so that's pretty nice. So the least squares regression equation is going to be given by this, and it's a unique linear combination of the explanatory or predictor variables, and it has the maximum possible correlation with yi. So we're saying we have the maximum possible correlation between yi and yi hat. Okay, we're going to maximize that by minimizing SSE. So if you remember that SSY is equal to SSR plus SSE, and SSR is the explained variation. And so if we have this amount of SSY and it's fixed, because once we take the sample, that's fixed, that's how much there is. Then if we minimize the SSE, make small, and this is constant, then we maximize the SSR. We make it as big as possible. And so SSR is how much is explained by the regression equation, and if you remember, this is directly related to the correlation. So all the possible linear combinations of, let's say, of this form, we're using little b for beta, the actual value of beta. Okay, so b0, b1, these are not the solved for values. These are all the possible values that we could put in there for each of them. So all of those possible ones, we are coming out with the maximum possible correlation, or the minimum SSE, of all the possible combinations there. And so that means that the correlation, which I've written down here, the correlation between yi and yi hat, but I'm giving it as, this would be vectors basically, is given as, so it's y, which is the vector y, which is all the y's, is given by this equation, sum of yi minus y bar times yi hat minus y hat bar. There's no I there. So we're taking the average of the best fit of the y hats, the points on the line. And we're taking all those averages and subtracting them from each of the estimated values. And so we've got the same equation here that we have for the correlation coefficient R between x and y. So if you go back to chapter 6 and look, if you substitute in x here and x bar, and then, leave y and y bar, and then substitute in x, I, and x bar, and then do the same xi and x bar here, you have R between x and y. So this is the same form, but I hope you notice that this is way more complicated than the case of two variables. We've simplified it to make it easy to calculate. Oops, didn't mean to mark that out. We've made it easy to calculate because this value here is a number, but these values, remember, they're of that form. Actually, I should go, each one of those values is of that form. So this is a very complex statement that's been simplified very nicely to look just like any other correlation coefficient. And this, we're maximizing it, and this is called the multiple correlation coefficient. Okay? So that is what we're doing when we find the least squares line. And again, we use calculus, which is not required for this course, but those of you who know calculus, what we do is we take this quantity q and we end up with k different equations, because we take the derivative of q first with respect to beta 1, and then we take it with respect to beta 1 hat, and then we take it with respect to beta 2 hat, all the way down to with respect to beta k hat, and we set these equal to 0 and solve, and we've got this system of k equations with k unknowns, so we can solve that usually and get a one value for all the individual beta hats, and that is the solution where we've minimized this. You can look at this, you can plot this and see that it's a parabola that's squared, and so we're minimizing. We're getting the point where the slope is 0, and the only place on a parabola that the slope is 0 is at the vertex, which is at the bottom, which is the minimum point. So we can also test this with the second derivative test or with the sign test using the first derivative test as well. So that's the process that we're going through. You don't have to know that for this course. I just want you to understand it the best you can. All right, so that's all we have for this video. I hope that it's explained this very well. Don't forget to scan in your lecture notes by midnight of the date listed on the course calendar. Update your formula sheet. You might want that multiple correlation coefficient and any other notes that you need. So if you have questions, come to our virtual office hours. If you can't, email me. Again, if you email me, send me pictures of your work and the problem, because I may not have it available. And that way I can help you through email. I hope you take care of yourself, and we'll see you next time.